Okay. So what we have done, we have drawn the schematic. Okay. So after drawing the schematic, we have to take the symbol of that. So for CMOS inverter, I will take a symbol. In this symbol, you will be having the functionality. Okay. So I have to verify whether my CMOS inverter is operating correctly or not. To verify this. So for that, what I have done, I have taken a symbol. So when you take a symbol, what are the pins you have used? That is your VDD, VIN, Vout, and ground. What are the pins you have used? That will come here. That is shown in the symbol. VIN, VDD, Vout, ground. So you can take your symbol of any form. You can redraw the symbol. Also, you can redraw like this. Okay. Redrawing the symbol is left to you. So you can redraw however you want. The actual representation of your inverter. But I have taken in a normal symbol like this: V in, ground, V out, and VDD. So first, what will apply for V in? So I want to verify whether the circuit is going to operate as inverter. Going to verify whether the circuit is operating as inverter or not. To verify that, I am going to apply this pulse waveform. Pulse waveform. Okay. What output I should get? I should get inverted out. I should get inverted out. Okay. When I see the pulse, I have two parameters, mainly two parameters. So one is your period, pulse period. Another one is pulse width, that is your on time. Pulse width, that is your on time. Okay. So now I will take a period as 20 nano. Here I have taken period as 20 nano and pulse width as 10 nano. So pulse width I have taken half of the period to maintain 50% duty cycle. Okay. So anyone, what is duty cycle? Anyone, what is duty cycle? It is on time divided by total period. Duty cycle equal to on time divided by total period. So your on time here is 10 nano. The total period is 50 nano. So you will get 0.5 into 100. 0.5 into 100 is 50. So to maintain 50% duty cycle, that is equal on time and equal off time, I am taking your pulse width as 10 nano. So when I maintain 50% duty cycle, your on time and off time both are equal. Okay. So this is what I want to apply for my V. So what I am going to apply for my V is pulse, V pulse, cadence. This component is called as V pulse. Call it as V pulse. Okay. Here what we have done, period is 20 nano and your pulse width is 10 nano. That you have to apply for your V. So next, other terminal of your V pulse, you are going to ground it. Symbol for ground. Impedance. You are going to ground it. That is negative terminal of your V pulse. Next, for VDD, I will connect DC voltage of 1.8 volt VDC is equal to 1.8 volt. So DC voltage. So in cadence, the DC voltage is represented by VDC. Pulse is represented by V pulse. DC voltage is represented as VDC. So for VDD, I will connect a DC voltage of 1.8 volts. Ground, I am going to ground it. I am going to connect for ground. And V out, I am going to connect for a pin. I will connect. So you have taken a symbol. After taking a symbol, you have drawn this test circuit. First, you have taken a symbol. After that, you have drawn the test circuit. This is your test circuit, because after by drawing this test circuit, you are going to verify whether this is going to work as Cmos inverter or not. So to verify that, what you have done, after drawing the schematic, you have taken the symbol and you have drawn the test circuit. In this test circuit, you have given the input as V pulse, VDD you have connected to 1.8 volts, ground you have grounded, and output is taken as a pin. Taken as a pin. So after this, what you will do, you will make types of analysis. Here, after this, you will make two types of analysis. So one is your transient analysis. So what is transient analysis? It is nothing but what is the output you are getting for the input. That's it. Transient behavior is nothing but what is the output you are getting for the what input you have applied. So that is nothing but called as transient analysis. Okay. So you already applied input as your pulse with a period of 20 nano, right? So you already applied pulse with a period of 20 nano. So means this is 20 nano, you will get one cycle. So in transient analysis, it will ask for a stop time. So you will give the stop time. That is, stop time means for what, till what amount of time this simulation has to run. Till what amount of time the simulation has to run. Okay. So it will ask for a stop time. This stop time, you give it as multiple of your period. Anything multiple of your period, you can give it. See, if you give as stop time as 40 nano in your simulation window, you will get two cycles, right? Because already you 20 nano you get one cycle. For 40 nano, you will get two cycles. If you give stop time as 60 nano, then you will get three cycles. In the simulation window, you will get three cycles. So like this, based on the stop time, you can select how many cycles you want in the simulation window. It's up to you. So better go with 60 nano or go with 80 nano. Get 4 cycles. Simulation window. Okay. So when this is your input V, applied to your Cmos inverter, what should be your output? So you will see the output as, that is V out is equal to inversion of you will see the output inversion of V. That is what you are going to do in transient analysis. But before doing the setup for transient analysis, when you are doing setup for transient analysis, you should give stop time as multiple of your period. Anything multiple of your period. What is the period you have given? 20 nano. You give anything multiple of your period. So better if you go with 60 nano or 80 nano. Okay. So this is about your transient analysis. So next we will see another type of analysis called as DC analysis. DC analysis. Okay. What is this DC analysis? See, you know you have an inverter. Inverter you have. Instead of applying V in as a pulse, instead of applying V in as a pulse, what I will do, I will apply a DC voltage. For here, I will apply a DC voltage at the V in. After applying pulse, I will apply the DC voltage, and I will change the DC voltage knob. In your lab, you have seen the knob, right, for DC voltage. I will turn the DC voltage knob from 0 to 1.8. I will increase my DC voltage from 0 to 1.8. I will change from 0 to 1.8. DC voltage. So if I change from lower value to most highest value of voltage, lower value is 0, most highest value is 1.8. So I change from lower value to most highest value of the voltage. What is the output you are getting? What is the output you are getting? So that is called as DC analysis. DC analysis is nothing but, so you apply the DC voltage to the input and change from the most lower value to the most higher value. Most lower value here is 0 and most higher value is 3. Change it from 0 to 1.8. Increase the voltage from 0 to 1.8. So if you do so, what is your output? VI. So this analysis we will do for all the circuits, what I mentioned before. So this is called as DC analysis. But while performing DC analysis, when you see here, you already applied V pulse. You have already applied V pulse. Again, you have to change that V pulse to DC voltage, and you have to increase from 0 to 1.8 voltage, and you have to record what is your Vout. Instead of doing that, you have a method in your cadence tool. You have a method in your cadence tool to perform DC analysis. So here, what happens here is that cadence will ask what parameter have to make DC analysis. What is the component? What is the component you have to use? What is the component you have to use to make DC analysis? You have the options there. So if you click on that component, automatically your screen will go to this test circuit. What we will show you, automatically your screen will go to this test circuit. So which component you have to make it as, which component you have to change to DC to do DC analysis? That is your V pulse. You have to change your V pulse to VDC, and you have to sweep from 0 to 1.2. Right? So I repeat once again what I have told. We have a test circuit with V pulse. Again, to do DC analysis, what I have to do? I have to replace this V pulse. I have to connect DC voltage, and I have to sweep from 0 to 1.2. Instead of doing this, we have an option in cadence, that is, in DC analysis, select a component which you are using for DC analysis. When you click on that, automatically the window will go to this. So in this, which source you have to change for DC? This is a source which you have to change for DC. So click on this source and change to DC. Okay. So this thing will change to DC only for this analysis. only for DC analysis. It will not change here. It will not change here. It will not change in the test circuit. It will, this V pulse will change to DC only for DC analysis. Okay. Next, it will ask your sweep range, starting and top range. So it is, you give it as 0, that is least voltage, and sweep range is from least voltage to maximum voltage. Maximum voltage you give it as 1. Sweep range give from 0 to 1.8. Okay. So when you sweep like this, what is the waveform you are getting? So you are sweeping your wheel. Your wheel, your, so finally what your output will be? Finally, what your output will be? So this is your curve. You are sweeping from 0 to 1.8. 1.8 input. Your input, you are changing from 0 to 1.8. And what is the output for this? The output for this is, you already studied 5 regions of operation. So the output you are getting. This is the output what you will get. So you know the 5 regions of operation which you have already studied. So this is region 1, region 2, this point is region 3, region 4, last is region 5. You have studied. Okay. So when your Vin is very low, so you are changing your Vin from 0 to 1.8. When Vin is very low, the output is high. When Vin is high, your output is low. Okay. Your output is low. So this point called as switching threshold. Called as VH. This point is called as switching threshold. So at this point, your V in is equal to V out. At this point, your V in is equal to V out. For correct design, for appropriate design, this should be equal to VDD by 2. Should be equal to VDD by 2. For correct design, this should be equal to VDD by 2. So this is what the waveform you should get for your DC analysis. Okay, when you change from 0 to 1.8, your V in, if you change from 0 to 1.8, you see when you, this is your V in, changing from 0 to 1.8. To 1.8. For that, what is your output? Output will be like this. Or like this. So when your V in is very low, the output is very high. When V in is very high, output. So this is about your DC analysis. So these two analysis, that is your transient analysis and your DC analysis. These two analysis you are going to do for your Cmos inverter. So what is the procedure you have to follow? First you have to draw the schematic. First thing, this one you have to do. After that, you have to take the symbol. Second procedure. Third thing is draw the test circuit. And last thing is perform these two analysis. Transient and DC analysis. At last you will get the waveform. You can verify the waveforms. Any doubts you have, students? Any doubts? Sir, Arvinda sir?
Okay, I'll proceed. Deepak, you can mute yourself.
Yes, sir.
So, students, I'll ask you questions now. Deepak has already discussed about how we have to proceed with the simulation of the inverter circuitry. Now, I'll ask you a question. Anybody can unmute and you can answer. If x-axis is uh, time and y-axis is output, what do we see in the curve? I am repeating the question. If x-axis is time and if y-axis is output, what do we see in that plot? Anybody can answer.
Time domain analysis.
It is time domain analysis. Fine, but what do you see? When you plot it, what do you see on the screen? Kuldeep has told inverted pulse of input. Yeah, that is fine. That is as far as the inverter is concerned. I am asking a very general question for any given circuit. A general question. Let us say x-axis is time, y-axis is output. What do you see on the screen? It's a single word. The answer is waveform. If x-axis is time, y-axis is output, you will see the waveform of the output. Now let us say if x-axis is input and y-axis is output, what do you see on the screen? Someone has to unmute and answer.
Curve.
Yeah. Tell me. If x-axis is input, y-axis is output, what do you see on the screen?
Is it curve, sir?
Which type of curve?
Linear or non?
Huh?
Linear.
A linear is fine. Kuldeep has put it as transient curve. No, it is not transient curve. It is transfer curve. Transient has something to do with the waveform, or transient has something to do with the shapes or timings of the waveform. Now, if x-axis is input, y-axis is output, you will see transfer curve on the screen. My last question is, if x-axis is frequency and if y-axis is output, what are you going to see on the screen? If x-axis is frequency and y-axis is output, what are you going to see on the screen? No answers? You are going to see the frequency response, gain and bandwidth response. In fact, in AEC lab, you had done this earlier where x-axis was frequency and y-axis was output. That means y-axis you used to have gain in dB and you used to plot it. You used to see the frequency response. Now I asked you three things. If x-axis is time and then x-axis is input and x-axis is frequency, y-axis remains the same. Y-axis is always the output. Now these three are basically called as three types of analysis. If x-axis is time, y-axis is output, then it is called as transient analysis, where you will see the waveform. And if x-axis is input, y-axis is output, then that is called as DC analysis, which is nothing but transfer curve. Now if x-axis is frequency, y-axis is output, you will see the frequency response and gain and bandwidth curve. Now Deepak discussed about transient analysis and DC analysis. He did not discuss AC analysis. Now you will have to tell me, students have to tell me, why he did not discuss AC analysis with respect to the inverter. Some of you only have to tell me. Okay, no answer. Then I'll only tell you. Why he did not mention about AC analysis with the inverters is because inverter is a digital logic circuit. For a digital logic circuit, we don't really measure its gain and bandwidth. There is nothing called gain for an inverter. And we only discuss about the highest operating frequency for an inverter. We don't apply a frequency response curve. But whereas when we discuss the analog circuits such as amplifiers, there we have to go for gain and bandwidth curve. So when we discuss amplifiers, there will be all these three analyses there. For an amplifier, we will have transient analysis where we want to see the waveform, and we will have DC analysis where we want to see the phase shift through the transfer curve, and we want to see the gain and bandwidth response, and there we go for AC analysis as well. Now, we will come to the last part of the lab now. I will discuss a few more things about how do we conduct the lab. I am going to share the lab manual now with you. Let me tell some basics now. We have this lab manual here. This MS Word file is not clearly opened out. There is a flow chart there in the lab manual. Later we will send it to you also. Now we have been discussing the analog design, simulation and layout. Now schematic entry can be done by means of direct through Verilog. I am not able to see this, whatever is there printed on the screen. Verilog A or through Spice Netlist. Either directly through a circuit diagram entry, that is possible. That is the method we are going to follow. We are going to have a Spice simulation there. Or through Verilog A, this I mentioned in the beginning, but we are not going to try out Verilog A. Or through Spice Netlist. If already someone else has done a circuit diagram, someone else will use the netlist. Generally in the industry, what happens is a great work or big work will be divided among many engineers. In a team, there will be somebody who will do only the schematics, there will be somebody else who will do only the verification of the schematics, and there will be somebody who will do only the layout of the schematics, and somebody else will verify only the layout of the schematics. Because the project will be too large and one person cannot complete it if only one person is given the job. That is why there will be teams. But in the lab, you will be doing it on your own. So in the lab, we are going to directly enter the schematic through circuit diagram. We are not going to use Verilog A or we are not going to use Spice Netlist as such directly. For simulation, a test circuit along with the symbol of the schematic is required. Just like in Xilinx lab, HDL lab, you had a Verilog code, then you had a test bench. Test bench itself also was a Verilog code. Using the test bench code, you used to test the main design. Same way, here in the custom design or in the analog design now, you will have a main circuit diagram and you will have a test circuit diagram. In the main circuit diagram, you will have only the basic circuit. In the test circuit diagram, you will apply the voltages, you will apply the input signal and you will plot the output signal. That is how we proceed. Now, it is possible that without the test circuit also you can directly test. That means, using a single circuit diagram. For that circuit diagram itself, you can give the input signal and you can plot the output. That is possible. Still, we go for a method where initially we will have a main circuit diagram. Later on, we create a symbol for that, and using the symbol, later on, we create a test circuit diagram. The reason is we are not going to manufacture the complete test circuit diagram. We are going to manufacture only the main circuit diagram. For example, today you saw an inverter circuit, only Pmos and Nmos. We are going to get only the inverter getting manufactured. We are not going to apply the input signal and plot the output signal, that VDC and Vpulse, all those things we are not going to get manufactured at all. So when we send the layout to foundry, that layout should contain only NMOSFET and PMOSFET with all those nodes and connections. There should not be power supply in the layout. There should not be Vpulse in the layout. Isn't it? That is why what we do is, we do only a main circuit and then we test it separately. When we have to make a layout, we will make a layout only for the main circuit. We will not make the layout for the test circuit as such. That is why it is better that we separate it. Simulation is separate, layout is separate. And it is better that we only keep a main circuit. Then whenever we want to simulate it, we will have a symbol and a test circuit. That is a better procedure. Now later on, DRC, LVS, RCX form parts of the physical verification process. DRC stands for design rule check, and LVS stands for layout versus schematic, and RCX stands for RC extraction. Right now, don't worry about these things. We are going to discuss this in detail when we start the layout classes. Now let me come to the initial procedures. Till now, Deepak mentioned about how to have an inverter circuitry and how to have its simulation performed. But in the beginning, before you go into Cadence, you are going to work with an operating system called Linux. You are not going to work with the Windows software in the Vlsi lab. The reason is, Windows software is highly prone to viruses. It is not secure. That is the first thing. Second thing is, Windows is not actually a open license software. Windows is licensed to Microsoft, and we are all using the pirated version of Windows. If there are bugs in the Windows, then it may affect our functionality of the circuits also. There are already enough bugs in the Windows, right? That is why every now and then new version of the Windows will be released and the old bugs will be removed. And in the new version, there will be some new bugs. For the new bugs, again after about 2 to 3 years, they will release one more Windows version. This will go on like that. We cannot depend on an operating system which will keep changing every now and then. Why? The reason is, once we design a chip using a particular software, that design should be applicable even for the next 10 years or 20 years. Let us say today I design an operational amplifier for a 180 nanometer technology. 180 nanometer technology will remain for the next 10-20 years also, because it has remained from past 20 years also. So when I design an op-amp, it will not become obsolete all of a sudden. It will be used in products. So it has to be accessible even in future. Now if Windows itself changes, the software itself changes, how do I import or export my designs when the operating system itself is changing? Now because of these reasons, all the EDA companies or the VLSI chip design companies, they don't depend on Windows at all. They always depend on Unix and Linux platforms. Unix and Linux platforms are time-tested platforms, means they will not hang now and then. Just like Windows system will hang, Linux or Unix systems will not hang. They have gone through thorough beta testing. And Linux is basically a open source platform, which means there is a team of people who keep on correcting this online directly. They will keep on removing bugs now and then directly without actually changing the software itself. That provision is there with Linux. Such provision is not there with Windows, because Windows is owned by a company. Linux need not be owned by a company. Even if you become an expert in operating system, even you can contribute to the development of Linux. That is how All the EDA companies use only Linux. They don't use Windows. Even in our lab, we use only Linux. Let us say you put a pen drive into the system. Even if your pen drive is having a virus, system will not get affected. The reason is Linux will simply detect the files in your pen drive, and even if you transfer your files into the system, Linux will identify them and it will label them in a different fashion, so that those files will never be executed by Linux. But in Windows, any malicious software can get executed because Windows does not check each and every file that way. But Linux will sense all those files, check all those files. That is how Linux is very secure. And we are using one version of Linux called Red Hat Enterprise Linux, RHEL. Now you may ask me, when Linux is a freeware, if it is an open source, why do we have this Red Hat? There are companies like Red Hat and Ubuntu. They develop a front end for Linux. At the back end, Linux remains the same. If at all you revise or if at all you understand the workings of the operating system, there is something called shell and there is something called kernel and there is something called user interface. At the outermost layer, there is a user interface. At the middle, there is something called shell. At the center, there is something called kernel. Now, as far as Linux is concerned, kernel and shell will remain the same. At the outer side, when there is user interface, either a company called Red Hat or a company called Ubuntu, they will develop the front end designs. Just like Visual Basic and C++ can be used together, where Visual Basic can develop a front end for user interface like a screen or keys or buttons. At the background, it is the C++ program running. Same way, Linux will be running at the background. At the front end, just to give a visual interface, Ubuntu and Red Hat companies will develop their user interface. That is why it is called Red Hat Enterprise Linux. In our lab, we are using Red Hat. Now, in the beginning, of course, you are going to do all this when you come to the lab. I am just giving you an idea about why should we go for such procedure as such. In the beginning, when you log into the computer, you will right click and you will open terminal. What I would advise is those who have a laptop and desktop at your home, you can as well install Linux also in your laptop. You can have a VMware there. Through VMware, you can have two OSs. Along with the Windows, you can create one more small partition and you can install Linux also in your system. So that using Linux also you can start working. You will become more familiar with Linux. For those of you who have the aspiration to get into VLSI industry, it is a must that you must be thoroughly familiar with Linux. Because in the industry, they don't use Windows at all. So it's a good thing that if you learn Linux on your own, it is better for you. We cannot teach you all the Linux related things in the VLSI lab. We are going to teach you only some basics of Linux. But if you become thorough with Linux, even for a placement, it is going to help you because it is going to give you a value addition. Apart from VLSI companies, there are other companies also which will be using Linux because of the problems which I told about Windows. Windows will have problems forever. Forever, because as long as a software is owned by a company, the company only will try to correct the errors in its own way. So Windows will not become Linux, become like Linux even in future. Windows will remain Windows, Linux will remain Linux. But Windows has its own advantages. Windows anybody can use without any specific training. For Linux to be used, it requires some training regarding the operating system itself. Especially technical people should be familiar with Linux. Just like you are learning Java, you are learning Python, you should learn Linux as well. That is my suggestion. Now, when you start this lab, after logging into the system, you will right and you will open terminal. That open terminal is in Linux. Then you will have to get into a C shell in Linux operating system. In Windows also shell is there, kernel is there, but that is not visible there. In Windows, always you will have some icons. You will double click on the icons and you will open up an application. But in Linux, you will have to get into a shell there. Because in Linux, there can be many shells called C shell or Bourne shell. You can also develop a shell for Linux. Now, I told you about user interface. User interface is like a visual platform or visual front end wherein the user will have access to the kernel. Now, what is shell? Shell is basically a command interpreter. In the sense, kernel is completely an executable version of an operating system, which is completely in the binary form. Whereas we use our mouse and keyboard and we use commands using English language. Now, this English language has to be transferred or transformed or translated into the executable format by the machine. So, there is something called shell. In the beginning of the days when Windows was invented, before Windows was invented, it was called as DOS, MS-DOS, Microsoft Disk Operating System, where there used to be DOS commands, Disk Operating System commands. Like for changing directory, it used to be CD. For making directory, it used to be MD. All those commands we used to learn and we used to use the operating system. Later on, Bill Gates thought that such commands also are not useful for the layman. Layman cannot understand all types of commands. Then they developed a front end for the Windows and they started giving icons on the screen. Now anybody can double click on an icon and it will open up the application. Now if you want to open up a MS Word, you don't have to type any command there. Just double click on that MS Word icon, MS Word will open up, MS Excel will open up. It is something like that. Now in Linux, such front end work is minimal because Linux is not for customer satisfaction. Linux is not for customer luring or making the customer happy or making the life of the customer easy. That is not the idea of Linux. The idea of Linux is efficient functionality without any bugs, without any hanging, without any further problems. That is what is basically required with the Linux. So there is no beautification as such with the Linux when compared to Windows. So in Linux, you will have to open the terminal, you will have to learn some of these commands. So when there are multiple shells which are available in Linux, we are going to use one particular shell called C. There is one more shell called Bourne, B-O-U-R-N-E, named after one of the scientists. We are not going to use Bourne shell in our lab, we are going to use C shell. As I told you, just like Red Hat and Ubuntu, there are different companies developing front end. Similarly, there are different companies developing shells also, but kernel will remain the same. Kernel of Linux will remain the same. So we are going to get into C shell. For that, we have to type a command CSH. Directly on the terminal, you will type a command CSH, which stands for C shell. That's all. Immediately, Linux will understand your command. Linux will get into a C shell without telling you. It will simply go next line. If it goes to next line, it simply means that it has gone into C shell. Next, we have one file called CSHRC. C shell run command is the full form for the CSHRC, wherein we have given some commands in our own way so that we can easily access this cadence tool whenever we want without typing commands every time. That is, all those commands are there in CSHRC. You need not be aware of all those commands, but whenever you come to the lab, you can open this file, you can see what are those commands there. But you should not alter any of those commands because they are all system related commands. So what we have done is, we have kept all those commands in a batch file. That batch file, we have named it as CSHRC. Sometimes we call it as chsrc.main also. Now, whenever that particular batch file is invoked, the commands which are there in the batch file are going to be executed immediately so that cadence tool will be executed. That is the idea there. So, The next step is run the shell script by typing the command source root/cadence/csshrc. We have kept that file in a folder. In Windows, we call it as folder, and in Linux, we call it as directory. Please remember these terminologies. Whatever you call it as folder in Windows, we call it as directory in Linux. Actually, when MS-DOS was there they used to call it as directory only. Later on, Bill Gates changed its name as folder, simply to have a difference between Unix and Windows, because Unix was there much before Windows also. The smaller version of Unix itself is Linux. Unix was used in mini computers, whereas Linux is used in desktop now. That's all. Otherwise, Linux is a smaller version of Unix only. Unix is a time-tested operating system which will never hang in its lifetime. So now, there is a command called source, and when you type this source /root/cadence/csshrc, the commands which are present in the csshrc batch file are going to be executed. Later on, you will have to move to a directory that is called cd, change directory, because you are right now with the root directory. In the beginning, you will always be in the root directory. I will show you one small picture. Now you will have a file structure like this. You will have many such file structures like this. It is like an inverted tree where you can have directories like this. Now this is root. Just visualize an inverted tree. In an inverted tree, root is at the top, and from the root we go down. We can have branches, we can have sub-branches, we can have sub-branches. At the end, we will have leaves or flowers or fruits. In the same manner, when you log into the system, you are in the root directory. Later on, you can go to some of the branches. Those branches are other directories. For example, this cadence is one directory. So you keep on going on to those directories. Again, you can keep on creating your own directories later on. In the digital experiments, we are going to tell you to create your own directories. Now, through the directories, at the end, you will have your own files. Just like in the tree, you will have leaves. At the end, in each directory, you will have files. You will have different types of files. For schematics, for Verilog coding, for synthesis, you will have different types of files. Just like a tree will have leaves, it will have flowers, it will have fruits, something like that. So, initially you will be in the root directory. Now you have to move to a directory called cadence_ms_labs_613. You don't have to worry about the full form of all these MS Lab 613. That is the name which Cadence people themselves have given, because there can be hundreds of directories now. The tool is a very big tool where it will have hundreds of directories, lakhs of files, not thousands of files, lakhs of files. That's why I told you in the beginning, Cadence is a licensed software, it's a custom designed software, and it is not available freeware. You have to depend on the college only for this purpose. Now you may ask whether the college paid 1 crore to Cadence. No. The reason is, from the university side, from the VTU itself, there was a regulation that all the colleges should have Cadence installed, and for which the Cadence has to give a subsidy. So, as far as college is concerned, we pay around 10 lakhs for 3 years. It is a subsidized price only for the sake of education. But we have signed a contract with Cadence that we will not use this software for any manufacturing activities. We will use this software only for education purposes. That is why, even though we have a Cadence tool, we cannot use it for manufacturing activities. We cannot send any of these designs to a foundry. Someday, if Cadence comes to know, it will put a case on us, because we have signed a contract that we are using it only for the education purpose. That is why we have been given a subsidy. It is from the university level itself. So, you cannot have this software at home at all. There is no chance as such. Okay, you will have to depend on the college lab only. Whereas companies, when they buy this software, they invest crores because they want to have licenses for manufacturing itself. Now, you will have to use the command cd for changing directory. Remember this, cd stands for changing directory. Then you will go to a directory called Cadence MS Lab 613. Later on, you will have to invoke the analog design tool. Cadence is divided into two parts, digital design separate, analog design separate. For the digital design, the tools which are used are different, and for the analog design, the tools which are used are different. Now we have a tool called Virtuoso. Virtuoso is the tool utilized for analog designs exclusively. And then we give a symbol ampersand. When we give a simple ampersand, what happens is, initially you have opened your terminal, right? The terminal also has to remain. Virtuoso also has to come into picture. Now, if you don't give the symbol ampersand, what happens is, Virtuoso will open up. At that time, it will hide the terminal. If it hides the terminal, you will not have any access to the commands now. When you don't have access to the command, you will not be able to know what is actually happening at the background. If at all you have to correct something, you will not be able to correct it when the terminal is not accessible to you. Now, if you give this symbol ampersand, Linux will immediately understand that the previous work also should remain as such. So, terminal also will remain, Virtuoso also will be invoked. Whenever you have problem with Virtuoso, you can go back to terminal and check there about what has gone wrong there. That is the reason we use this symbol ampersand. After the Virtuoso console opens up, you can maximize it, then the Linux terminal can be minimized. Still it will be accessible in your taskbar below. At the bottom, even the terminal will be accessible. Now in the Virtuoso console, you have to create your own library by following the steps. File, new, library. I am showing you a snapshot here. You will have this file. When you click on this file, it will ask new. There will be a pull down coming here. In the pull down, new will come. When you pull down, when you click on new, it is going to ask you library or file. You are going to create one new library. In your own way, you can create your own library because you can keep all your files in that particular library. So, initially you will be creating a file, new library. Now, in the new library, when it opens up, you will have to click an option called attach to an existing technology library. Now, remember this. What is the meaning of technology library? I have told you the meaning of technology is 180 nanometer technology. Here technology does not mean a general word. In general, technology means technique and logos. Logos means knowledge, technique means method. But here when we say, in the VLSI lab when we say technology, it is actually referring to either 180 nanometer technology or 90 nanometer technology or 45 nanometer technology or 22 nanometer technology, so on. In our lab, we have all these three. We have 180 nanometer, we have 90 nanometer, we have 45 nanometer. But we still keep teaching 180 nanometer only. Why? The reason is 180 nanometer is a very stable technology which was tested from last 20-30 years. Whereas 90 nanometer technology and 45 nanometer, they are not fully tested. There are issues even in those technologies. Now in the 22 nanometer and 10 nanometer, there are enough errors which industry is facing now. Now they are thinking of going back to the previous technologies only because the newer technologies have newer issues. Okay, that apart, we are going to teach you only 180 nanometer and you will have to attach your library to a 180 nanometer technology library because when you make a PMOS and a NMOS, you are simply extracting the symbol of PMOS and NMOS. You are not going to have a complete mathematical model for a PMOS and NMOS. That mathematical model will have more than 200 parameters. Now, you cannot write a model for a MOSFET simply like that. Now, Cadence has got this model developed by the research teams or it has taken these models from the research teams. I mentioned about the Berkeley University in USA. They are even now working on the MOSFET models. There are many engineers working on latest MOSFET models. So a MOSFET model can contain more than 200 parameters. You cannot access any of those parameters. They are all patented models. Now Cadence will simply put a MOSFET symbol. That's all. In the library, when you access, you will simply pick up a MOSFET symbol, just like you have been working with the PSpice. Now when you pick up a symbol, that symbol contains internally 200 parameters, which you will not be knowing. Now those 200 parameters are actually mapped for 180 nanometer technology. That is why your design has to be attached to an existing technology library. That is 180 nanometer technology library. That is the step which is this. I am telling all these things in detail. Please don't forget all these things. Please remember all these things, because when an offline lab starts, immediately we will be asking you to start your practical sessions directly, hands-on. At that time, we will not have the time to discuss all these things once again, because the time will be scarce at that time. That is why we are discussing all these things in very much detail. You will have to remember them. If possible, have an observation book with you. In the observation book, keep on noting down, because at the end, we will have marks for even observation book, right? For your attendance, there is 1 mark. For your observation book, there is 1 mark. For your record, there is 1 mark. Now, we don't know whether we are going to relax your record rating or not. Right now, we have not taken such decision. But it is always advisable that you have an observation book with you, 100-page notebook, and you keep on noting down whatever we are discussing in the lab, so that you will remember these things. And at the end, we will ask you to show your observation book. At least we will feel happy that you have been noting down whatever we have been discussing. Otherwise, if you don't note down, if you simply keep listening to whatever we say, then through 1 year you will listen, through 1 year it will go out after 1 week. Unless you make an effort to write down, you may not be able to listen, or you may not be able to remember everything. You are not Shakuntala Devi, I am also not Shakuntala Devi, right? We don't have such great memory which Shakuntala Devi had. So naturally, I keep on telling these things because out of my own teaching experience, now I have remembered everything. As students, you will not be able to remember everything just by listening. It is better that you note down. Now, attached to an existing technology library, afterwards, these are all the snapshots. You can always go through this manual later on. Now, a selection box named Attached Technology Library will open. Select GPDK 180 and click on OK. What is this GPDK 180? Generic Process Design Kit 180. It is a generic process. Now, Intel will have its own foundry. Sony will have its own foundry. Samsung will have its own foundry. Many multinational big companies, they will have their own foundry. When they have their own foundry, those processes are not generic processes. Those processes are meant for their own products. Whereas, for us in India, only in Chandigarh we have this 180 nanometer foundry. Otherwise, we don't have other foundries. In BEL, Bharat Electronics Limited, they also have a foundry. That foundry is meant for military products. It is not meant for commercial purposes. If we have to send our design to Chandigarh, or if we have to send our design to China, then that is a generic process. We cannot ask Intel or Sony or Samsung to get our IC manufactured, right? They will not care for our design at all. They will have much bigger designs. So, anyhow, we are not going to get it manufactured. I am just giving an example. If any small company wants to manufacture an IC on its own, it cannot request Intel or Sony or Samsung. It has to depend on either Chandigarh's foundry, SCL, Semiconductor Complex Limited, or they have to depend on foundries that are present in China. So that way, that is going to be a generic process. That is why this is called GPDK, Generic Process Design Kit 180 nanometer. Then when you click on OK, your library will be attached to GPDK 180. Later on, you can easily pick up a PMOS FET and an NMOS FET, which are meant for 180 nanometer GPDK. That is what is this process about. Now later on, for design entry in the Virtuoso console, again click on File, click on New, click on Cell View. I will not bore you further. In the next 5 minutes, I will stop. But I want anyone to answer now for this particular question. I am going to ask you only one question now. I am not going to ask you any more questions. This particular question, what is a cell? Can somebody answer? In the VLSI domain, what is a cell? Anybody? Somebody? Everybody? Okay, Kuldeep says a group of transistors. Somewhat all right, but not very accurate. Yeah, tell
A
me.
group of transistors combined with logic gates.
Group of transistors combined with logic gates. No, it can be analog also. It need not be digital. A cell can be analog also. We are right now discussing analog designs. A group of transistor is correct. It need not be for logic gates. It can be for any other functionality. It can be digital functionality. It can be analog functionality. Now, this group of transistors, it is not just transistors. The layout of transistors is also made and it is available as in the layout form in the library. That means when you pick up a PMOSFET, the PMOSFET's layout is already made by the Cadence people. Along with the source, drain, gate, polysilicon, oxide, everything, substrate, everything, metal, everything. Now, when you pick up a PMOS, you are simply seeing only a PMOS symbol. But basically, PMOS layout is also available there. Now, that is called as a cell. Cell need not be a group of transistors. It can be a single transistor also. So, I will define the cell as a pre-designed, pre-characterized library element. Please remember this. Please note down. A cell is called as a pre-designed and pre-characterized library element. In general, we use this word cell in many ways. Even for a jail, we say jail cell. If a prisoner is there inside the jail, we will say cell number 3, cell number 5, something like that. What does it mean? That cell is a room in the jail where the prisoner is supposed to sit. And that jail cell is characterized for a prisoner stay. Similarly, we call red blood cell, white blood cell. What does it mean? That red blood cell is characterized for its functionality, white blood cell is characterized for its functionality. They remain inside the blood, but they remain separate as separate cellular entities. A red blood cell will have its own micro organs inside. Even a white blood cell will have its own genetic material inside. They will have DNA, RNA, and everything else inside. But they are distinctly different as far as their functions are concerned. So, a cell is a smaller structure, smaller element of a bigger structure, we can say. For example, if you visualize a bundi laddu, just visualize a bundi laddu. Bundi laddu is made up of so many bundis. Each bundi is called as a cell now. Now the bundi laddu is made up of a combination of ghee and dry fruits and bundis. But each bundi is distinctly different. At the same time, there is a replication of so many bundis there. Same thing with motichur laddu. In motichur laddu, you will have so many small motichur pieces. But together it is becoming a motichur laddu. Same way with kesri baat. In kesri baat, you will have small rava particles, broken wheat particles. But together it is a kesri baat with ghee and dry fruits and all those things. Now let me come back to technology. Let me not take you to the kitchen. Let me come back to technology now. Now in the technology, again we have P MOSFET, N MOSFET. Now these are the basic elements in the VLSI design. Now for this PMOS and NMOSFET, it is not the symbol which is important for us. It is the source, drain, gate and all those substrates and the metal and oxide and polysilicon and N-type diffusion, P-type diffusion. All that is a layout now. That layout is going to be manufactured. The symbol is not going to be manufactured, right? Symbol is only for our purpose, for engineers to use it as a circuit diagram, in the circuit diagram. Ultimately, when it gets manufactured, it is going to have all those physical layers of silicon and the dopants. Now that has to be characterized. The layout has to be characterized. Now a cell is containing a symbol, it is containing a layout, it is containing its own predefined characterization. That is why I define a symbol as a pre-designed and pre-characterized library element. It is already designed, it is already characterized for 180 nanometer technology and it is present in the library. That is called as cell. Now you are going to create your own cell view for your inverter. In the inverter, you are going to pick up two cells called Pmos and Nmos. That is the meaning of this. So file new cell view because you are going to create a cell called inverter on your own. In that new file form that opens, browse for your library name in front of the cell, fill in the name of the schematic. For example, inverter. You are going to give the name, an inverter, for the cell which you are going to create. I hope this much is enough. Now it is already 10:30. We have been continuously talking from 8 o'clock till 10:30. The remaining things along with the schematics in the next class I am going to tell you, and in the next class me and Deepak are going to tell you how from cell view we will gradually perform simulation and gradually we will go into layout. So see you in the next class. I have recorded this session from maybe from 9:30 onwards, I don't know. Whatever is recorded, I will upload it to Google Drive and I will share the link in the lab WhatsApp group. If anybody has any other questions, you can ask me. Otherwise, we will close the session now. Anybody has any questions? No more questions. Already students have started leaving the meeting. Fine. Me and Deepakar. Anyway, let it be. Let me end the meeting.
Yes, sir. Thank you, sir.
Okay, sure.